Welcome back. We're on part 3 of 3 when it comes to our techniques of integration. So this is it. We're going to finish our toolkit today, and if I have time, I'll summarize the whole methodology. That's going to take my going quite quickly for the first hour and 40 minutes. I'm going to have to cover a lot of stuff. I'd like to have 20 minutes to go through a little overview of all the techniques so far and in which order you should try them. Next week we're going to do something completely different, which I believe is volumes. So for the moment then, let's talk about trigonometric integrals. So I'm going to talk about trig substitutions. That's my focus. But most integrals involving this trig substitution, whatever that is, I'll get to it, but most integrals involving trig substitutions lead to an integral that is involving trig functions, or a power of one of our favorite trig functions. So I thought I'd spend the beginning part going over some techniques of how to integrate certain powers of trig functions. And there's different techniques depending on what the trig functions are. There are more combinations than I can possibly even cover, but nevertheless, the most common ones are things like powers of sine, cosine, tangent, secant. So that's what or even cosecant and cotangent. So that's what I want to start off with. So here goes. Let's start off moving in chapter 19, section 19.2 of my book, looking at powers of sine and cosine. So I'm going to show you how to do an integral that looks like this. Say sine to the power nx, cosine to the power mx dx, where these are, say, integers, positive integers. Now, this also includes powers of sine. If m happens to be 0, okay, positive integers or 0. So it also includes powers of cosine, and it includes combinations, some power of sine, some power of cosine. Now here's the technique. If one of them is odd, seize it, grab it. Grab the odd power. It is your friend. And if they're both odd, take the least of the two. So if it's sine to the third, cosine to the fifth, the third is better than the fifth for what I'm going to describe. So grab least of the two, lower if odd power. If they're both even, I'll tell you what to do a little later. If there is if one or both, n, m is odd. So grab the lower of the two, if you can, or whatever one is odd, and steal one power away. So that what's left is even, right? If you take one power away from an odd, you're going to get an even. So pair this stolen one with the dx and use a trig identity. Well, what on earth does that all mean? In order to show you, I'd like to do an example. Suppose you want to do cosine to the 7th x, sine to the 10th x dx. Well, I've got two powers, 7 and 10. 7 is the odd one, so I'm going to seize that. I'm going to steal away cosine x and put it with the dx. So what's left is cosine to the 6th x, and then I'll have a cosine x dx. The fact that there's a cosine x dx suggests that I should substitute t equals sine x, because dt is cosine x dx. Of course, there is stuff in sine x, so that's just t to the 10. However, I've got to change the cosine into a sine. So what I want you to do is think of this as cosine squared x all cubed. See, if after all, since the 7 was odd, I stole one power away, I get an even power, and that allows me to write it as cosine squared x to some power. Even numbers are divisible by 2. So, of course, I can change this before I do the substitution into 1 minus sine squared x all cubed, because cosine squared x is 1 minus sine squared x. Now, everything except for the cosine x dx is in terms of sine x, and sine x is just t. So this works out to be 1 minus t squared all cubed times t to the 10th dt. After all, cosine x dx is just dt. All right, well, we still have a little bit of work to do. What I'll do is expand out the cube and get 1 minus 3t squared plus 3t to the 4th minus t to the 6th. It's really handy to be able to do that. Just know the coefficients 1, 3, 3, 1, t to the 10. This is admittedly a fairly nasty example, but totally beyond the realms of possibility, in Math 104 at least. So, you get all these powers here with the various coefficients. It's just a polynomial. And you can integrate. You get t to the 11 over 11 minus 3t to the 13 over 13 plus 3t to the 15 over 15 minus t to the 17 over 17 plus c. And all that's left is to replace the t by sine x again. So you'll get sine x 11th power minus 3 sine 13th power. I guess 3 over 15 I'll cancel to 1/5. And then there's a 17th power plus a constant. That same technique is going to work for any time when one of the powers is odd. It actually even works if the other power is any number at all. If you look at it, suppose instead of sine to the 10x, I had any other power. Doesn't matter what the power is. Instead of this t to the 10, I'd have t to some other power, and when you multiply it all out, you'd still get powers of t, which you can integrate. Okay, so as long as one of them is odd, the other one is irrelevant, really. But the odd allows you to steal one away and do that trig identity. Okay, so you've got to practice these things. You can practice them. You can just write down, integral of cosine to the 5th x sine any power. Or try actually integral of cosine, your favorite number in there, whatever you feel like. Could be huge, could be fractional, whatever, times sine to the 5th x dx. That's a little exercise. You fill in the blank and work it out. Check your answer by differentiating. All right, any questions about that? Yes?
So this question you said was within the realm of 104?
Oh, absolutely.
Okay.
Absolutely. No, it's within the realm of possibility, but it sort of takes a little bit longer because you have to expand out that factor here. I mean, if you had cosine to the 9th x, you'd have a 4th power you'd have to expand, and that would get messier and messier, right? So the higher the odd power is, the worse it gets. That's why you pick the lower power, in fact, if you have 2 odd powers. All right, so moving along, what if they're both even? If they're both even, this trick just doesn't work. If both powers are even, you've got to use the double angle formula, or formulas. Here they are. You ought to know that cosine squared x is, let me write it this way. I have to work this out in my head. No. Let's do it like this. 1 plus cosine of x. There we go. Back on track. Okay, I'm going to put a box around these because you have to know them. Now, actually, if you just look at this one, if you mentally multiply it by 2 and subtract 1, you get the equation cosine 2x is 2 cosine squared x minus 1. That's the standard double angle formula. Now, sine squared x, of course, comes from that. In fact, if you add them up, you get cosine squared plus sine squared. Here you get 1, because it's a half plus a half, and these other terms cancel out. So this is, you've seen this before, but maybe not in this form. This is the form you need to do integrals of this sort and other similar integrals. So when I say use this, let me give you an example of how to use it. What do I want to do? Cosine squared x sine to the 4th x will do. Let's try doing this integral. Well, the prescription calls for finding an odd exponent, but 2 and 4 are both even. So we'd better bust out the double angle formulas. According to these formulas up here, cosine squared x is 1/2 1 plus cosine 2x. However, I'm going to think of the sine to the 4th x as sine squared x all squared. That's the same as the trick we did before when we thought of cosine to the 6th x as cosine squared x all cubed. There's always the square in here, by the way. 2 and 2 are the same. The other one makes it a little clearer. I don't know if we can scroll back over here where it says cosine to the 6th x. That's cosine squared x all cubed, not cosine cubed x all squared. You could write it as cosine cubed x, but that would be useless. All our identities are for squares, cosine squared. So in this case, we have just the square of sine squared x. So what is that? Well, we have to take 1/2 of the second line, 1 minus cosine 2x, and square all that. And unfortunately, we're just going to have to expand 1/2 all squared. You're going to get 3 factors of 2, which gives you 1/8. You'll have 1 plus cosine 2x, and we might as well multiply out the square here. You get 1 minus 2 cosine 2x plus cosine 2x all squared dx. Now, unfortunately, we've got one more multiplication to do. Oh, let's just multiply everything by 1 first. 1 minus 2 cosine 2x plus cosine squared 2x. And now plus cosine 2x. What do we get? Cosine 2x minus 2 cosine squared 2x plus cosine cubed 2x dx. And I guess we can simplify that a little bit. We'll have a 1. How many cosine 2x's do we have? There's a bit of cancellation. You get minus cosine 2x. Cosine squared 2x, I believe we also cancel out a little bit. And there's just the cosine cubed. We've still got more work to do, lads. We've still got more work. Not that much, but a little bit. 1/8 outside of, well, the integral of 1 is just x. The integral of cosine 2x, well, what's the integral of cosine x? Plus sine x, not negative sine x. Derivative of sine is cosine. So the integral of cosine 2x would be 1/2 of sine 2x. Of course, we have a minus sign out the front, so it's just differentiate this to check. You get cosine 2x times 2, cancels out the 2. No extra minus. Unfortunately, these two still need to be filled in. So I'm going to do our old trick of leaving a bit of space. Let's take a working column over here. I think I can fit these in. First of all, we have to integrate cosine squared of 2x. Well, now we've got a power 2, which is even. We've got no odd powers. The power of sine is 0. It's not there at all. That's unfortunately also even. So we have to use the same identity, the first one above, but instead of cosine squared of x, we have cosine squared of 2x. So that means wherever you see x, you have to mentally replace it by a 2x. So according to that, this is 1/2. I'm bringing it out of the integral already. 1 plus cosine of 4x, not 2x. And as I've said, the integral of 1 is x. The integral of cosine 4x is sine 4x over 4. And actually, we can pull this piece in over here with a minus sign in front of it. But we still have to fill in the last piece. So the last piece, we now need to integrate cosine cubed of 2x. How are we going to do that? Well, this time we do have an odd power. Cosine cubed. 3 is odd. So C is this, busted up into cosine squared 2x times cosine 2x dx. Replace this using the trig identity by the sine, 1 minus sine squared 2x. We still have a cosine 2x dx. Now the substitution is t, lots of working columns here, nested working columns. T is sine 2x. Careful, dt is 2 cosine 2x dx. Here we have a cosine 2x dx. dt is twice that, so if you divide by 2, you will find this integral in t land. Actually, I don't need to squash it down here. I'm just going to keep working across here. So I'm going to have 1/2 that comes from the dt. Careful of that. That's really essential. You get 1 minus t squared dt. Once again, dt over 2 is cosine 2x dx. So this is a fairly straightforward integral. It's 1/2 outside of t minus t cubed over 3 plus a constant. And that, when t is sine of 2x, this becomes 1/2 sine 2x minus 1/6 sine cubed 2x plus a constant. Now I've filled this in up here. 1/2 sine 2x minus 1/6 sine cubed 2x. I don't know whether to put the parentheses around. Maybe I should. Okay, there's a little bit of simplification left. I don't know. Sine 2x over 2. Sine 2x over 2. They actually cancel out quite satisfyingly. X minus 1/2 x. That helps a little bit. You'll just end up with 1/2 x. I think you get 1/16 x. And then you've got a sine 4x that doesn't get matched, times 8 times 2 times 4. So that should be minus 1 over 64 sine 4x. And we'll also have 8 times 6 is 48. It's possible I've made a mistake. Maybe I wrote down for myself what the answer was to check it. X over 16 minus a 64th sine 4x. How about that? I seem to have gotten it right. So this is actually the final answer. The rest was working. So actually, if you think about it, cosine squared sine to the 4th was a lot worse than cosine to the 7th sine to the 10th, even though the powers are low. Again, practice makes perfect. And you see the interesting varieties you can have when you just replace x by 2x or some multiple of x. You get these other factors popping out that you have to be careful of. All right, that's enough about powers of sine and cosine. Anyone has a question, please start shouting it out. I'm afraid you just sort of have to learn these techniques. It's not the most interesting part of the course. It's nice to know that it's doable. But it is just sort of remembering a technique and then knowing how to do it. Same's going to go for tan. Let's look at powers of tan. Okay, so I'm looking at an integral that just looks like tan to the nx dx. Okay, well here's some simple cases. Tan x itself, we know we can write that as sine x over cosine x. The derivative of the bottom is the top, except for a minus sign. So maybe we should put in a minus here and then a minus out the front. And now, ignoring the minus out the front, the derivative of the bottom is the top. So as we've said, the answer is just log of the bottom, absolute value. And we'll have a minus because of the derivative of cosine being sine. Okay, so the first power of tan isn't too bad. Pretty standard. What about tan squared x? Well, tan squared is secant squared minus 1. So I'm going to use that identity. And the integral of secant squared just happens to be tan x. The integral of 1 is x, so you get tan x minus x plus c. So that covers the first two powers. But I'm not going to stand here and do all the powers because it would take me forever. Instead, what I'm going to do is show you how, in principle, to do any power that you like. Now, here's the idea. For higher powers, steal tan squared and convert to secant squared x minus 1, just like we did for tan squared, this previous integral. So convert that to secant squared x minus 1, multiply out, and you get two integrals. One will involve secant squared, and the other one won't. The first one, you let t be equal to tan x, and it works because dt is the secant squared that you just generated. So that's easy enough to do. Whereas the second one, the second integral, is a lower power, so repeat the whole process. That's the game plan. Once again, it's just a plan. It doesn't really mean much until we see how it works. The example I want to do is tan to the 6th x, but I'm not going to do the whole thing. I want to show you how it starts and leave you with a little work to do. So suppose you want to look at the 6th power. Okay, according to my prescription, you steal away a tan squared. So this will give us a tan to the 4th. And we have another tan squared that we have the tan squared that we stole away. Now I'm going to convert this into secant squared minus 1. And now I'm going to break it up into two integrals. One is tan to the 4th x, secant squared x dx. And the other one is tan to the 4th x. Okay, let's operate on this one first. So maybe I'll do my old trick of leaving a blank. And I'll come over here and I'll operate on tan to the 4th x secant squared x dx. Let t be tan x. That's specified in my process above. dt is secant squared x dx. And guess what? We have that sitting right there. So this is just equal to t to the 4th dt. Tan to the 4th, t to the 4th, secant squared x dx is dt. So this works out to be t to the 5 over 5 plus a constant, which is the 5th power, tan to the 5th x over 5 plus a constant. Well, we don't need the constant when we plug it in up here, because I'm going to put tan to the 5x over 5, I'm going to leave this integral. We don't need the constant right now because that integral involves one. Now here's where you come in. You get to do this. You see, notice that we started off with the 6th power of tan, and as a result of these shenanigans of trig identities and stealing away and all that sort of stuff, splitting up, we now have only the 4th power. In fact, every time you apply the method, you knock the power down by 2. Eventually, you'll either get down to the 1st power or the 2nd power. And we've just done those up the top. So actually, you have to repeat the method. So equals blah. You fill this in by doing tan to the 4th x yourself. Steal away a tan squared, and you'll get tan squared x. Another, here's the stolen one. There's the leftovers. And in this one, we'll convert it to secant squared x minus 1, etc. You have to finish it off, split it up, and then one integral, you do the t equals tan x again. The other one's just tan squared, and we already know how to do that. So it's a recursive sort of process. If you had to do tan to the 11x, you'd have to find tan to the 9, 7, 5, 3, and finally tan x itself, the integrals. Okay? So it just takes a long time. So you're unlikely to get much bigger than a 6th power, because otherwise you'd just be doing it forever. There is a thing called recursion formulas or recurrence formulas. I do cover them in the book, but they're not really in the Math 104 course, so I don't have much time. Well, I don't have any time realistically to spend on them. But they allow you to automate the process, basically, by finding a formula to get you down to the next level, and then you just kind of apply it without actually writing down any more integrals. It's a pattern. That's all it is. Worthy of study, but I don't have time. Okay, so that's how you do powers of tan. Again, practice. Do that tan to the 4th, and try tan to the 5th for good measure. If you can do that, you can probably do any power of tan with enough time and persistence. Anyone have any questions about that as I'm erasing the board? This stuff isn't really in the textbook, I don't think. It's sort of embedded in exercises, and yet it seems like you're supposed to know it, so that's why I'm taking the time to go through all these techniques here. Anyway, I'd like to talk about powers of cotangent just for a few seconds. Cotangent, if you should happen to see it, it's the same, except you put co in front of everything. The equation you use is cotangent squared x is cosecant squared x minus 1. Just be careful when you integrate. For example, the integral of cotangent x by itself, well, that's cosine x over sine x. And this time you don't need a minus sign, actually. The derivative of sine is cosine. So this is just log of sine x. On the other hand, if you do the square, you use the identity. So you're dealing with cosecant squared x minus 1. But be careful. The integral of cosecant squared x is minus cotangent x. As for higher powers, again, you steal away a cotangent squared and replace it by cosecant squared minus 1. Split up the integral and everything else as before. Okay? I'm not going to spend any more time on it because I don't have it. I don't have the time. But you need to practice doing integrals of cotangent. Very, very similar. And there's some information in the book as well. I forget which section. It's over there. My notes are over there. It's in 19.2 point something. Anyway. All right. We've got to move on to powers of secant. We're getting close to the end of this whole thing. Powers of trig functions. But I have to show you powers of secant. And this one, I'm afraid, is the worst. This is worse than any of the others. Powers of secant. Let's start off with the first power. And in some sense, the first power is the most difficult. There are a number of ways to do this. But my favorite involves a trick that is just so ridiculous, it's a miracle anyone ever thought of it. You see, speaking sarcastically for a while, you do the obvious thing when faced by an integral like this. Yes, you multiply by secant x plus tan x and divide by the same quantity. This, to me, if you didn't think of this, then you must be pretty slow. Because, I mean, look at it. Isn't that what you'd obviously do? Yes. Yes, I think any 3-year-old would work that out. Okay, enough sarcasm. This is just a ridiculous trick that happens to work. There's probably a good reason why someone thought of it, but I actually never thought about it myself. I just marveled at the beauty of it, because if you expand this out and write it as a fraction, then a minor miracle occurs, because you see, the derivative of tan x is secant squared x, and the derivative of secant x is secant x tan x. So the top is the derivative of the bottom, and the answer is just the log of the absolute value of the bottom. There's probably some interesting calculus history about how that sneaky trick was first derived. But in any case, you can either remember the trick, or you can maybe remember just the answer. It is on a standard table of integrals. It's a sort of gray area as to whether you're allowed to just quote it. For my mind, if the question was find the integral of secant x, you would probably want to show some working. But if the integral is more complicated and involves this, you might be able to get away with it. I'm not grading your exams, and certainly if you're watching on the internet doing some other course in the future, I'm not grading your exam, so I don't know what's legitimate. This is the sort of thing that you could just ask, hey, can I just write down the integral of secant x as this, or do we need to prove it every time? Might as well clarify it. Anyway, that's the quickest way to do it if you need to show working. There's a partial fractions method, all sorts of ways, but that one's kind of cool. On the other hand, having done a really nasty trick, or a clever trick, to find secant x, thank goodness, secant squared x, we don't have to do anything other than write down the answer. No trig identities, no tricks, just tan x. Unfortunately, it's all downhill from here. After this, higher powers. Okay, bear with me. It will hopefully become clearer in example. Steal away secant squared. So far, so good. But you've got to resist the temptation to write it as tan squared x plus 1. Instead, you've got to integrate by parts with dv is secant squared x dx, and u is everything else. You see, then you'll get v is tan x. So you've got to integrate by parts. That's the first thing. Steal away secant squared x and integrate by parts. But even after you do that, you'll still have work to do. So maybe I'm going to leave a space and start my example, and then I will fill in the rest of the method, because I fear if I give it to you all now, it'll just be a meaningless pile of gibberish. It'll just be mumbling stuff. So I am going to start off an example, which may well be the 6th power again, if I'm not mistaken. The cube is the most common, of course. but I choose to show you the 6th power because if you can do that, then you can do the cube. Right, so suppose you were faced with having to find the 6th power. And as I think this is just about the nastiest that you could possibly be expected to do. Probably worse than even you would have to do. But, you know, just trying to cover your ass here. So, integral of secant to the 6th is secant to the 4th secant squared x dx. Now, as I said, I want you to think of this as dv, and everything else will be u. So let's see. U equals secant to the 4th x. dv is secant squared x dx. So v is tan x. du is 4 secant cubed x. That's just the 4th power. Unfortunately, you also need a secant x tan x dx, because the derivative of secant is secant x tan x. So I guess that simplifies to 4 secant to the 4th x tan x dx. Okay, now we've got to integrate by parts. This is equal to u v minus the integral v du. And let's fill in the blanks using this stuff. We get secant to the 4th x. V is tan x minus the integral of tan x. And du is 4 secant to the 4th x tan x dx. Whew. Okay, let's just write this as secant to the 4th x tan x minus 4 integral secant to the 4th x tan squared x dx. Now, if you've remembered things up this far, the only thing you really needed to remember was steal secant squared and integrate by parts. The rest took care of itself. However, maybe you think you need to know what the next step is. I don't know. To me, it might be fairly clear. The fact is, no matter what the original power of secant is, you will always get a tan squared x. One comes from the v, and the other one comes from the du. So we always get a tan squared x, and we're going to write this as secant squared x minus 1. So the next step is, I'm just going to sort of have to, unfortunately, oscillate between the boards. After, use tan squared x equals secant squared x minus 1, split up integral. Okay, well, let's do it. When you multiply this out, you're going to get a secant to the 6th and a secant to the 4th. So let's do it. We get secant to the 4th x tan x minus 4 secant to the 6th x. That's from this 4 and the 2. And then the minus 1 will just give us a secant to the 4th. And because of the minus out the front, we'll have a plus. All right. All this is equal to the integral of secant x to the 6th. I'm just copying the left-hand side. We've seen this before sometimes. When you integrate by parts, sometimes you get the original integral coming back out again. So let's put it on the other side. Let's add 4 times the integral of secant to the 6th to both sides. And this will give us 5 times the integral we want is secant to the 4th x tan x just plus 4 integral of secant to the 4th x. And you divide by 5. And you get the 6th power is 1/5 secant to the 4th x tan x plus 4/5 the integral of secant to the 4th x. All right. As a result of all this, we have once again knocked down the power by 2. We started off with the 6th power. Now we have a 4th power. And again, I say to you, I'm leaving you some work to do. Do the 4th power. It's the same. Very similar. Just the numbers. You don't get a 4. You don't get a 4 when you differentiate because you don't have a secant to the 4th. You get a secant squared. So wherever you see a 4, you'll basically get a 2. The numbers will be a little bit different. In fact, when you add the 4 over, you got a 5. This time when you add the 2 over, you'll get a 3. So there should be thirds around. Okay? But you have to do it. And after you've done it, you will knock it down to secant squared. But that is the end of the road because secant squared is just, the integral is just tan x. Okay? Then, after you've done that, you can try the 5th power. You'll knock it down to the 3rd power and down to the 1st power. And if you can do that, then, hey, you've mastered the secant integrals. And I've seen them come up in Math 104, particularly the 3rd and 4th powers. I was being a little bit extravagant with the 5th and the 6th, but, you know, I want to give you something to do and to finish this off. So let's just go back to our method and just finish it off. First integral, put first integral on left-hand side to combine with original integral. Right, because the first integral that comes out is just the original power of secant x times some constant. You put that over on the other side and divide by the coefficient. Divide by the constant out the front. In that case, it was 5. And you've reduced the new integral is 2 powers lower. So, unfortunately, rinse and repeat, except without the rinse. For the benefit of those on the video, few people did snicker at that. Tough crowd. All right, so there's the method. Any questions about it? Sort of speaks for itself, really. Practice. Okay, well, let me just say, the good news is, the last type, powers of cosecant squared, or cosecant x, same trick. Everything that works for secant also works for cosecant. You just have to be careful of the minuses. Right? So, for example, to do the first power, you multiply, here's the same sort of trick, you multiply by cosecant x plus cotangent x. Same silly trick, except that when you do it, you will find the derivative of the bottom is the negative of the derivative of the top. There's one step missing, and you should get minus the log of cosecant x plus cotangent x plus c. Similarly, the integral of cosecant squared x is just negative cotangent, and the higher power is the same. I'm not going to write out the full method because it's so similar. You just start off, steal out cosecant squared x dx and call this dv. It's again integration by parts. The difference is this time v, you have to integrate cosecant x, so v will be negative cotangent x, etc. So the minuses and pluses are in different places, but otherwise the solutions are the same. All right. Those things you just have to practice. Excellent. So as I said, I'm going to skip, it's actually 19.2.6 is the reduction or recursion formulas. It has multiple names. I don't have time to do it. Instead, I'm going to move straight on to trig substitutions, which is really the main reason, in a way, to do all these integrals that we've done so far. So many trig substitutions lead to them. Now, they sometimes are useful by themselves, but they do seem to come up quite often in applications in real life from trig substitutions. So, pause for breath. All right. Working in section 19.3 of my book, trig substitutions. Okay, this is, as it sounds like, a form of substitution that involves trig. Well, it doesn't tell you how to do it. In fact, let me give you some sample integrals that would involve trig substitutions. I'm just going to write down 3 integrals, which we will solve in due course. Dx over x cubed, square root of x squared minus 4. So that's one integral. X squared over 9 minus x squared to the 3 halves dx. And x squared plus 15 to the minus 5 halves dx. All right, what do these have in common? The answer is that they all involve the square root of a quadratic. They all involve a square root of a quadratic. So that is a hallmark of a trig substitution. Now, this one, you can see it very clearly. There's the square root, x squared minus 4. This one, it's a 3 halves power. Well, another way of writing that would be the square root of 9 minus x squared all cubed on the denominator. And similarly, you could write this, actually the minus 5 halves, you could write the whole integrand as 1 over square root x squared plus 15 to the power 5. So you should be on the lookout for square roots of quadratics or quadratics to the 3 halves, 5 halves, 7 halves, 9 halves, etc. Why not 2 halves? Well, that's just 1. It's not a square root. So it's got to be an odd multiple of a half to be a square root. Okay, so if you have a square root of a quadratic, you probably need a trig substitution. Before I even tell you what they are, let me show you an exception. Suppose I modify this top one slightly. X over x squared minus 4. You could use a trig substitution, but we already know how to do this. You see, the derivative of x squared minus 4 is just 2x. So I can let t be x squared minus 4. dt is 2x dx. And there's the x dx. And I'm going to leave just etc. You'll just get 1 over root t times dt. So with a half floating around as well. So that's a fairly straightforward integral. So sometimes you can avoid a trig substitution if there's a derivative floating around. Look out for that. You can save time. Doesn't really apply, obviously, in any of these cases. Maybe you can do it in some unobvious way. But here, you know, the derivative of x squared minus 4 is just x. It's not there. It's x to the x cubed. Same thing here. If there was an x on the top, sure, let t equals 9 minus x squared, and it's pretty straightforward. But with x squared, not so easy. And this one, there's nothing else floating around. So don't always use trig substitution when you see a square root of a quadratic. Try an ordinary substitution first, or at least consider it. Most of the time, you're out of luck. You have to go on with this method. Now, there are really 3 different types of quadratics. What I like to do is just pretend, for the moment, that there's no linear term. It's just a quadratic term, like an x squared, and a constant. There's no x stuff. And these 3 examples all fit that bill. Later on, I'm going to tell you how to deal with the x stuff. And yes, it does involve completing the square, and not much else. But for the moment, let's say there's no x stuff. Look at these 3 quadratics. Here you have the square root of x squared minus something. Here you have the square root of something minus x squared. And here you have the square root of x squared plus something. Those are the only 3 possibilities. You couldn't really have minus 9 minus x squared, for example? Why not? I know I've done all the talking so far, basically, but why couldn't you have minus 9 minus x squared? Yeah, it's negative. Minus 9 minus x squared is always negative. Can't take the square root. So there's really only 3 types. You might think that 15 plus x squared is a different type from x squared plus 15, but of course, it's the same thing. So let's look at the 3 types one by one. I'm actually going to start with the middle type. I forget whether I call them A, B, or C, or 1, 2, and 3. I call them 1, 2, and 3. So type 1, I'd like to start off with when your integral involves something minus x squared. Now that something has to be positive, as I've just discussed. And so rather than write just a, I'm going to write it as a squared. So in our example, in the middle one from above, if we can just look at that middle integral up there, you have 9 minus x squared. Although there's a 9, I really want you to think of it as 3 squared. So in that example, as we shall soon see, a should be 3. All right? So how do you deal with this? Well, the trick is to make the substitution x is a sine theta. You could use t, but it's just, you're dealing with a sine, and you take sine of angles, and angles are Greek letters and all that. So you have to know that x equals a sine theta. Well, a here is a constant, so you're going to need dx is a cosine theta d theta. Okay. Now why is this substitution going to work? Well, notice that you have to take a square root of a squared minus x squared. So let's just look at the quantity a squared minus x squared. Well, a squared is a squared, but x squared is a squared sine squared theta. Let's factor that into 1 minus sine squared theta, and wouldn't you know it, you get a squared cosine squared theta. That's a pain to take a square root of, but this is a pleasure to take a square root of. Basically, it's just a cosine theta. So your integral is going to eliminate all the square roots when you do the substitution. Now, I'm going to jump ahead a little bit and tell you that you're going to go from x land to theta land when you do this substitution. And I will show you with this exact example up above how it works. So you're going to go from x land to theta land. Eventually, you have to go back from theta land to x land. And you're going to have, most likely, a whole bunch of trig functions of theta. So how do you go back from theta to x land? You're going to need a triangle. Here is the triangle. I'm going to draw a theta. And I'm going to notice that sine theta is x over a. What does that mean? Sine theta is x opposite over the hypotenuse. And now I'm going to use Pythagoras' theorem to fill in the missing side. It's just going to be the square root of a squared minus x squared. And guess what? That's the quantity that is in the integral. So you pretty much, if you don't get something that matches, you've made a mistake. Now this triangle allows you to tell me what's cosine theta, what's sine theta. Well, we already knew that. But tan theta, cotan theta, any trig function you can just read off. So what I've done is I've showed you the working without actually the integral itself. But the good news is that the working for this type, at least, is the same no matter what the integral is. The only difference is the value of a. And if you can actually do all of this first before you even start the integral. And you'll have everything you need at your fingertips. So let me show you how it works in practice. What I'm going to do is solve this integral up here. It's the integral of x squared over 9 minus x squared to the 3 halves dx. And I'm going to follow this exact prescription. except instead of x equals a sine theta, I'm going to have x equals 3 sine theta. Because as I said, a squared is 9, so a should be 3. So let's just, I'm going to end up generating this, but you don't even really need to remember it. You just need to say, okay, once you've written this down, you obviously need to know what dx is, like any substitution. So it's 3 cosine theta d theta. And you're also going to need to know what 9 minus x squared is in order to do this. So 9 minus x squared, you just write it out. It's 9 minus 9 sine squared theta, which is 9, 1 minus sine squared theta, which is 9 cosine squared theta. We're just going to need that. It's just going to pop out. Now, we could just do the integral, but I like to think ahead. I know I'm going to need the triangle, so let's just draw the triangle. Theta, sine theta is x over 3. So I'm going to put opposite is x over hypotenuse is 3, and of course I get square root 9 minus x squared. I'm not going to use this until a little bit later, but it gives me some peace of mind to write it down. So let's do the integral. Let's worry about the numerator first. What's x? X is 3 sine theta. So the numerator is 3 sine theta all squared. How about the dx? Dx is 3 cosine theta d theta. How about the denominator? Well, we know that 9 minus x squared is 9 cosine squared theta. So let's just plug this in. And we got a 3/2 power there. Okay, we've successfully changed every x that was in the original, including the dx, into theta and d theta. So we've migrated from x land into theta land. And we don't need to find clever bits of derivatives because the method doesn't tell you that something, something, something dx is d theta, like we normally do. It just tells you exactly what dx is. You just replace the dx by something. Okay, so we have a little bit of work to do. We're going to get a 9 sine squared theta. We still have a 3 cosine theta. 9 to the 3/2. You've got to be good with your exponentials here. 9 to the 1/2 is 3. It's the square root. And then cube that. So you get 27. Now cosine squared theta to the power of 3/2 is cosine cubed theta. We've actually taken the square root. So technically, there should be absolute values here. However, I cannot get bogged down in technical details. The fact is that you do not need them. It turns out that the thing is always positive. And it's not obvious why. And I spend some time in 19.3.6 to justify why you don't need it. But again, it's a sort of technical point. So with some misgivings, I say, okay, I'm just going to give it to you. You're taking a square root. You can't just take square roots and just replace them, right? I don't want you to write this. That's not true. The square root of minus 3 all squared is the square root of 9, which is 3. So it's not true that you square something, then take the square root, and you get the original back. It's only true if it's positive. And it turns out, just because of the way the trig functions work, and the quadrants and all that, that yes, this is positive anyway. So, without worrying about it too much, let's see what we get. Actually, the 9 and the 3 cancel out with the 27, as it turns out. Cosine theta kills off 1 power, and you get cosine squared theta. So we end up with sine squared over cosine squared, which is just tan squared. Now you see that we have a power of a trig function, and that's why I spent the first 40 minutes or so, 45, whatever it was, going through powers of trig functions. This one worked out to be secant squared minus 1. Well, that's what you had to do. And then you were going to get the integral of tan theta, not the integral, rather, the integral is tan theta minus theta plus a constant. Well, that's great. We've solved the integral, but we're still in theta land. Now, let's leave the first term. Theta, if you come over here, you see sine theta is x over 3. So the best you can really do with theta is to say this is inverse sine x over 3. Perhaps you are tempted to write here tan of inverse sine. But that's bad because you can simplify it. In fact, let's look at the triangle that we put in. If we hadn't drawn it before, we should draw it now, this right-angled triangle. Pretty bad right angle there, but whatever. What's tan theta? You just read it off the triangle. It's the opposite x over the adjacent, root 9 minus x squared. And we finished. All right, so let's think about this again. We have a type a squared minus x squared, so it's something minus x squared. We let x be a sine theta, in this case 3 sine theta. Dx just speaks for itself. We take this 9 minus x squared in this case, and we use the trig identity to get it down to a square. So that now when we put it in the integral on the bottom, we can take the square root, in this case as a 1/2 power, and then we have to cube it. Don't forget to do the same with the coefficients. You also have to substitute for any extra x's that are floating around, and of course the dx. And eventually you just get some trig functions or powers of trig functions spat out. And then you use the techniques that I taught you first. And you get the answer, and the thing you have to do is use the triangle to get rid of any of the trig functions that pop up. All right? Any questions about that? That's like a first prototypical example of a trig substitution that I'm giving anyway. If you have any questions, again, shout it out. All right. I'm going to move on to type 2. The good news is it's quite similar in principle. Type 2 is going to be square root of a squared plus x squared. Again, it doesn't matter which order you write this in, x squared plus a squared is the same as a squared plus x squared. The great news, as I said, is that the template is almost the same. It's just the trig functions that change. So in this case, the thing you absolutely sort of have to remember or identify is when you see this, you say, that has got to be x equals a tan theta. It's a different substitution because there's a different trig identity involved. I'll show you why it works in just a second. Dx is a secant squared theta d theta. That's the one thing, of course, whenever you write down a substitution, you need dx. But why does this work? A squared plus x squared is a squared plus a squared tan squared theta. So it's a squared outside of 1 plus tan squared theta. And look, there's the trig identity. 1 plus tan squared is secant squared. And you get a squared secant squared theta. Okay, you need a different trig identity for a plus. It happens to be the 1 plus tan squared, so there it is. So again, when we take the square root of this, which we will have to in our integral, we'll just have to take the square root of this, which will just be a secant theta. Again, there should be an absolute value. Doesn't really, it's not necessary. Just thinking ahead, we're going to need a triangle, but it looks a little bit different. This time, if you go back to the original equation, tan theta is x over a. And this time, tan is the opposite over the adjacent. So by Pythagoras' theorem, this will be a squared plus x squared. Again, that matches the type. You've made a mistake if it doesn't match. And again, from this, we'll be able to get back from theta land without too much trouble. All right. Let's do this integral. Integral x squared plus 15 to the power minus 5 halves dx. That's another one of the integrals that I wrote up there. Now, this is a bit messy because 15 is not a particularly nice number. Square root of 15 is just the square root of 15. So that's going to be our value of a. You might want to write that down. A is root 15, just to remind yourself. So according to this prescription, but again, not really memorizing it, just knowing what it's all about, the one thing you do have to really memorize or intuit is that you're going to need to start off with x is root 15 tan theta. It's just not, it's not an obvious substitution. I have to admit, I look at it, it's not obvious. The reason it works is because of the trig identity. But it's not, the reason this is a separate topic from substitution in a way is that the substitutions that you have to do here are not obvious. You kind of have to learn the three types. In any case, dx is going to be root 15 secant squared theta d theta. We're going to need to take x squared plus 15. So I like to put that in the working. As always, you're going to get 15 tan squared theta plus 15, which is 15 tan squared theta plus 1, which is 15 secant squared theta. And just for yocks, I'll put the triangle up first. Tan theta is x over root 15, which means that I have opposite of x adjacent of root 15, and by Pythagoras' theorem, this will be x squared plus 15. Great. We've got all the tools we need to finish the problem. So let's do it. X squared plus 15 is 15 secant squared theta. Take that to the minus 5 halves. dx, careful, it's not d theta, it's root 15 secant squared theta d theta. Now what? Well, let's deal with the constants first. We'll have 15 to the minus 5 halves from there. And we might as well write this as 15 to the 1 half. And then we'll have the integral. 2 times minus 5 halves is secant to the minus 5 theta. Again, it should have absolute values. It should have absolute values. It doesn't need it, though. Why? I'm not telling you. You have to read the book. Sorry about that. No time. Secant squared theta d theta is still left over. So what's going to happen is you've got a power of minus 5 there, a power of 2. The overall power is going to be minus 3, which, of course, is 1 over secant cubed which is just cosine cubed. So if you work this all out, minus 5 halves plus a half is the minus 2 power, and 1 over secant cubed is cosine cubed. There's a bit of extra working. Just have to be careful of your powers. This is, of course, 1 over secant to the 5th. So secant squared over secant to the 5th gives you a secant cubed on the bottom. But, of course, 1 over secant is cosine. So you end up with cosine cubed theta d theta. So that has transferred the integral from x land over to theta land. Well, how do you do it? Sorry? Yes, c is the odd power. In this case, it's cosine cubed. 3 is odd, so we pull out a cosine. 15 squared is 225, so I'm going to convert that into 1 over 225 integral cosine squared x, cosine x theta rather, cosine squared theta cosine d theta. Replace this by 1 minus sine squared theta. And substitute a further regular substitution, t equals sine theta. So dt is cosine theta d theta. And the integral becomes 1 over 225 integral 1 minus t squared dt. Cos dt is cosine theta d theta. So this is 1 over 225 t minus t cubed over 3 plus a constant. All right. Now, we've got to untangle the variables. Moving over here to give myself a bit more room, we get 1 over 225. What is t? T is sine theta. So you get sine theta and t cubed sine cubed theta over 3. That's a constant. Okay, so we've gone from t land back to theta land. We now have to go back to x land. But this is where this triangle up here comes in, because we can immediately see that sine theta is just the opposite x over the hypotenuse, root x squared plus 15. And for sine cubed theta, you could write just x cubed over the square root of x squared plus 15, all cubed, and you need a 3. That's okay. But I think we can be a little cleaner about it and write first term as it was, and this as x cubed over 3 x squared plus 15 to the 3 halves power plus a constant. I think that's the right answer. Yes, that's what I seemed to get before. Okay. How different is this from the first type? Not very. First type involves more sines and cosines, and yet the integral, who knows? The integral that you end up with could involve tans, because sines divided by cosines are tans. In this case, the substitution bit all involved tans and secants, and yet the integral still just came out to a power of cosine. So you definitely needed to know the techniques there. It could just as easily have come out as, say, an integral of secant cubed, and then you'd have to know my secant, the secant technique that I taught you. It's not my technique. I didn't invent it. I didn't invent any of this stuff. I just try to channel it from Newton, it's Leibniz, and whoever. Well, anyway, I don't claim to be possessed. Pretty sure I'm not, actually. What was that? Oh, sorry, I thought it was an apple. Oh, tough crowd. Tough crowd. Well, there's one more type. And that's the example I'm going to use, but I'll rewrite it. Type 3. So the only type left looks like x squared minus something. It turns out to be different from even x squared plus something. The identity that you need is a little bit different. In fact, this time, well, it is the same as the last identity, but this time you need to let x be a secant theta. Before I tell you why that works, let's just differentiate. A secant theta tan theta d theta. Now, x squared minus a squared is popping up. So what is that? That's a squared secant squared theta minus a squared. Factor out the a squared. And you get secant squared theta minus 1. As I said, it's the same identity, but this time we're using it in a slightly different form, and we end up with tan squared theta. Again, easy to take the square root. Triangle we'll need this time. It says secant theta. If you go back up to this equation, divide by a, you get secant theta is x over a. So this time the triangle says, well, cosine is the adjacent over the hypotenuse. So secant is actually the hypotenuse over the adjacent. And so this side will be the hypotenuse squared minus the other side squared. And surprise, surprise, you get the same thing here for the unknown side as you do for the thing that was in the integral that inspired you to use type 3. Hopefully. By the way, one little comment. It's not in any of the examples that I put up. But suppose that this was x squared minus 1. Well, a would be 1. And you just have x equals 1 secant theta, or just secant theta. And normally you don't write the 1, right? 1 times anything, you don't bother writing the 1. Sometimes it can be a little bit hard to see. This is just a bit of an aside. Maybe I'll throw it over here. Maybe we can just come up over here. If you happen to have a equals 1, chalk is a casualty tonight. If a equals 1, in any of these types, not just type 3, you'll have something like x equals, say, a sine theta for the first type, e.g., you would just write, in this case, x equals sine theta. And ironically, it can be hard to tell what the triangle should look like. See, you would just write sine theta is x. And sort of not so easy to see that you really need to write over 1, just to be really clear that the other side is 1. It's a sort of missing thing. You just don't write it. And yet you've got to put that in so that you get the root 1 minus x squared. And the same for the other 3. So just as a cautionary tale, if a is 1, do put it in the denominator of the trig function so you can see how to draw your triangle. And I'll leave it to you to draw what the other 2 types would be. That's the type 1. Type 2, type 3, similar sort of thing. Anyway, let's go back over here. There's the template for type 3. Let's go back and do the example that I put up before. Integral dx. Let me just make sure I get it right. X cubed root x squared minus 4. Before I start, I'm just going to say one little thing. What could the values of x be? Or what is x not allowed to be for this integral even to make sense? Well, in between negative 2 and positive 2, actually. See, if it's, which is pretty much what you said, but just paraphrase. So in between minus 2 and 2 is bad, because you'll end up with a square root of a negative number. You can't do that. So x either has to be greater than 2 or less than minus 2. So actually the antiderivative of this thing is sort of in two pieces. It turns out there is a complication with the square roots. Again, I've said I'm not going to talk about it. So instead of talking about it, type 3, if you want to do it properly, or at least if you don't want to muck around with absolute values, you'd better specify here that x is greater than 2. Let's just find the integral when x is greater than 2. You could also write x greater than 0, but that means x has to be greater than 2 anyway, because even if x equals 2, this denominator is 0. Otherwise, the denominator doesn't even exist between 0 and 2. So let's just solve that problem and be done with it. Now, I hope in Math 104 that whenever you have an integral in type 3, that we remember to put that in. Because otherwise, you do have to do the x less than minus 2 case, or minus a in general, separately, and you'll need a minus sign that comes out because the square root just does not work. I choose to ignore this because I've never seen this examined in Math 104 at Princeton. Not at least for the last 10 years. Maybe in other schools, I don't know. You do have to worry about it, in which case you better check out that section at the end of 19.3. Anyway, that said, there's an integral. I'm only going to find the antiderivative to the right of 2 and just ignore the rest. I'm going to follow the prescription again. X equals, well, here a is the square root of 4, which is 2. So x is going to be 2 secant theta. dx, as always, got to find that. So the derivative of secant theta is secant theta tan theta d theta. And we're going to need to know what x squared minus 4 is. Well, that is 4 secant squared theta minus 4, which is 4 outside of secant squared theta minus 1, which is 4 tan squared theta. And the triangle is going to be given by secant theta is x over 2. Secant is the hypotenuse over the adjacent. And Pythagoras' theorem tells us that the other side is x squared minus 4, which, of course, appears in the integral, and therefore we know we're on the right track. So there's our working, all ready for us. We haven't even touched the integral. Let's go and do it now. On the top, we have dx, which according to this is 2 secant theta tan theta d theta. Here we have an x cubed, so I'll write that as 2 secant theta all cubed. And here we have a square root of x squared minus 4. Again, from my working, I know that this is 4 tan squared theta. So I've converted everything to theta land. Let's do a little bit of simplification. Here I have a 2. There I have an 8. 2 cubed is 8. Square root of 4 is 2. Then I have an integral of, well, let's just write this out. Secant theta tan theta all over secant cubed theta square root of tan squared theta. This is where you can really see. You take the square root of tan squared theta, you should write absolute value of tan theta. You should write that because the square root of x squared is just absolute value of x. This turns out, in this case, to be positive but only because of this condition. That says, okay, it turns out, and again, it's technical, it's not so difficult, you can easily understand it if you take the time, but it turns out that condition ensures that tan theta is actually positive, and so you don't need the absolute values. On the other hand, if you did have to do x less than minus 2, in that case, tan would be negative, and so the absolute values, you'd need an extra minus sign. Anyway, in this case, we don't. That cancels out. That cancels out. And you get secant over secant cubed, which leaves us with a secant squared. And again, 1 over secant squared becomes cosine squared. These cancel out as well. You get 1/8 the integral of cosine squared theta d theta. Now that is a little bit different than the cosine cubed that we did in one of the previous examples, the type 1 example. So, how do we do it? Use the double angle formulas. You get 1/8. Cosine squared is 1/2 cosine 2 theta plus 1. Actually, I want you to learn it as 1 plus. That's how I wrote it up before. So that the sine one is easy. D theta. So if we work this out, we get 1/16. 8 times 2 is 16. We get theta. And the integral of cosine 2 theta is sine 2 theta divided by 2 plus a constant. So this works out to be 1/16 theta plus 1 over 32 sine 2 theta plus a constant. So we've now worked out the integral. We're no longer in x land, though. We have to switch back to x land from theta land. So the theta, I'm just going to write inverse secant x over 2. After all, secant theta is x over 2. So theta, best you can do is inverse secant x over 2. However, the sine 2 theta is a bit of a problem. Here we have sine 2 theta, but the triangle that I've just drawn up here only tells me what something of theta is. So how are we going to find sine of 2 theta back in x land? Sine 2 theta is 2 sine theta cosine theta. So you're going to have to know, in addition to all the other formulas, the double angle formula for sine, which we have not used tonight at all. This is the first time we've used this formula. So we'll get 1 over 32 times 2 sine theta cosine theta. Let's leave ourselves a little more room. We'll get 1/16. And now we come up to the triangle. What is sine theta? It is the opposite x squared plus 4, no, x squared minus 4 square root over the hypotenuse x times cosine theta, which is the adjacent 2 over the hypotenuse x. And so if you work this out, you get 1/16 inverse secant x over 2 plus 1/8 root x squared minus 4 over x squared plus constant. And then did I get that right? I believe so. Okay. Very good. So that's type 3. Again, very similar to types 1 and 2. You just start off with a different trig function, use a different trig identity, different triangle, but they're all the same sort of template. Now, you'll find in 19.2.5, if I'm not mistaken, a summary that consists of those 3 left-hand columns that I wrote. one for each type. So I'm not going to write out the summary since you already have it in different places. But there it is in the book, all in one place, just in case. Again, I don't want you to memorize it and then just sort of fill in the blanks. Instead, think about what you're doing. You do have to write down x equals a and the right trig function. Absolutely. You've got to get the type right and you've got to get the trig function. But then dx you just know by differentiating. And look at the integral and you'll see whether you need x squared plus a squared, whatever it is, or x squared minus a squared, and just write that down and simplify it. Finally, draw the triangle. Again, you don't memorize which triangle it is for which type. You just use the math and know your trig functions. Then you'll have all the tools you need, do the integral, and go back using the triangle. As you see, it can be a little tricky. Sometimes you need to pull out other identities. And so, of course, there's a lot going on here. So practice. A question?
What would you do if x is greater than or power of 2?
X is...
If x is 6.
You mean in this thing? Oh, you're saying underneath the square root? Well, first thing you should probably do is panic. But that's not really realistic. So the question is, suppose that your integral involves something like x to the 6th minus 9. Say, what I would try to do first is I would angle to substitute t equals x cubed. That's what I'd really want to do. Now that would, for this to work, I'm going to need an x squared sitting around for it to work. Now, let's suppose this was the problem. I don't know if this is going to work out, so I may not finish it. But suppose it was integral of x to the 5th square root x to the 6th minus 9. There's no nice trig substitution because that's not a quadratic. Instead, you have to do some preliminary manipulations. I'm going to put t equals x cubed for the simple reason that when I operate on this piece here, x to the 6th is the same as t squared. And I like squares. So that piece is going to become t squared minus 9. On the other hand, dt is 3x squared, so 1/3 dt is x squared. I left out the dx. So if I bust up this x to the 5th into an x cubed and an x squared, then the x squared dx is 1/3 dt. And luckily, what's left over is x cubed, which is just a t. Now, actually, that was a pretty silly example. That was a really dumb example, because the derivative of x to the 6th is just x to the 5th. So I'm going to cheat and change it to an 8, which is more difficult. If I change it to an 8, then after you steal away the x squared, you'll have an x to the 6th. And so that is actually t squared. And so you'll end up with this integral. So that is now a trig substitution. You would let t equal 3 secant theta. It's a type 3. And I don't know. You have to work it out. It'll take a while to work out, and you'll get the answer in theta land. You convert it back to t land, and then you replace t by x cubed. Now that will only work in certain circumstances. The power here had to be just right. It had to be a multiple of 3 plus the x squared for this to work. So 6 plus 2, for example. X to the 11 would work. But if it was x to the 7, I don't know. The thing could be, I don't think you could really do it. So if you have a 6th power, you have to be pretty lucky. If you just have a quadratic, on the other hand, it'll work most of the time. Okay? So the question was, what if you have some other power here, like a 6th power? Try a substitution first that reduces it to a square. Then you can maybe do a trig substitution. But that won't work all the time. All right? Now, here's what I'd like to do for the remaining half hour. We don't even have a full half hour. So what I'd like to do is quickly show you how to dispense with a linear term, if you have it in your quadratic, by completing the square. And then I'd like to just do a summary of all the integral types that we've done over the last 3 weeks, including today. So that's the plan for the rest. So let's just dispense with this linear term stuff. Right. Suppose you had an integral like this. I did not write this down in my notes exactly what I wanted to do, unfortunately. So now I have to try to reverse engineer it. So let's just do this. I'm just going to make this up on the fly, I'm afraid. I don't know, x squared plus 6x plus 24 to the minus 5 halves dx. Why not? Okay, this doesn't fit any of the types because of the 6x. That x term was not there. But you can convert it to one of the types by completing the square. So if you have a linear term, complete the square first. Let me show you how it's done. X squared plus 6x plus 24 is equal to x squared plus 6x plus something nice minus the same nice thing plus 24. What is the nice thing that you've put in here that goes nicely with the x squared plus 6x? Well, you divide the 6 by 2, and you get 3, and you square that. So the nice thing to put in is 9. Of course, you can't just add 9. You have to subtract it again. And then this becomes x plus 3 all squared, and 24 minus 9 is 15. So actually, we should come back to our original integral and write it as the integral of x plus 3 all squared plus 15, all to the minus 5 halves. Now, substitute t equals x plus 3. dt is just dx, and this works out to be the integral of t squared plus 15 to the minus 5 halves dt. So as a result of this sort of preliminary conversion using the completed the square technique, we've reduced it to a type 2 case. In fact, that's the same integral that we did before for the type 2 case, and I can't remember what the answer was, so I'm going to look it up. I believe it worked out to be 1 over 225, changing x to t, of course, t squared, t over t squared plus 15 minus t cubed over t squared plus 15 to the 3 halves power plus a constant. Now, of course, if you were just seeing the question cold, as opposed to after we'd already done this variation, you would have to fill in a whole lot of steps between there, the entire trig substitution stuff. But you've already got it, because I already did it, and you just replace x by t. Of course, now we have to get back to x land. T is x plus 3, so this will work out to be x plus 3 over square root x plus 3 all squared plus 15 minus x plus 3 all cubed over x plus 3 all squared, again, plus 15 to the 3 halves power. And we really ought to simplify this. There's no need to multiply this out because we've already completed the square. You just undo the completion. Undo the completing the square. It's just the original quadratic that we had. X plus 3, square root x squared plus 6x plus 24. Minus, and again, x plus 3 all cubed, x squared plus 6x plus 24 to the 3 halves plus constant. So actually that not needing to expand should be reminiscent of what we did in some of the partial fraction stuff last week. There, if you look at the bit at the end where we did a linear over a quadratic, we have to complete the square most of the time, and you often end up getting, well, you basically end up having to undo the completion of the square You could do it by multiplying it out, or you could just use your existing work and save a few moments, which could be precious in an exam. So there's trig substitution. 3 types plus 1 little completing the square technique if you need it. Most of the time you don't. When I say that, I don't mean in real life. I mean in Math 104 exams, just based on my experience. But 1 in 10 times, say, you do. So make sure you can do it. All right. Trig substitution's done. All techniques of integration that at least I have time to do are done. So, I'd like to spend the next 20 minutes having a stretch. Okay. You don't need to film him having a stretch. It's not a pretty sight. No, it's fine. It's fine. What we are going to do, what I'd like to do now is just go through the techniques. Now, I'm not going to do them in the order that we did them. I'm going to do them almost in the order that I would think of using them. Okay, so here's a review of integration. Integration techniques, not what integrals mean. We did that earlier, fundamental theorems. This is just the techniques, your toolkit. So, whenever I look at an integral, first thing I say is there an obvious substitution? And by that, I really mean, is there a nasty function of something, but its derivative is just floating there? Can I just do a substitution that is easily going to reduce the integral? Right? An example would be something like what I did before, x over, say, root x squared minus 9. Again, don't use a trig substitution. The obvious substitution is t is x squared minus 9 because its derivative is up there. So you're looking for derivatives of other pieces in there being multiple. The worst that happens is you try the substitution and you get a nastier integral and you abandon that. You can always, it's like a maze. You can get to dead ends and you can always just go back and start again. There's no one right way through it, obviously, for every integral. Sometimes you just got to try a bunch of things. Okay, one obvious substitution, though, in a way that may not seem so obvious, is if you have an nth root of a linear term like ax plus b, and I discussed this 2 weeks ago. If you have that sort of thing, and this is contrast this with the square root of a quadratic. This is the nth root of a linear thing, where n could be any number, 5th root, 7th root, 23rd root. If it's a linear thing, let that be t. That's a good substitution that should work. Not guaranteed. Right? Again, I'm not going to spend much time, I'm not going to spend any time on going further because I've already done it, but I'm just trying to give you a sort of overview of what we've done. Now suppose that it's a rational function. Integral p of x over q of x. Well, I hope that you would have tried the obvious substitution, which in this case is maybe the derivative of the bottom is the top, in which case you should already have done that. You just get the log of the bottom. And I did talk about this last time. But otherwise, and that has to be you have to be lucky for that to happen. If it doesn't happen, you've got to use the partial fractions, and we spent all last week talking about it. Now, suppose your integral involves 1 plus cosine x or 1 minus cosine x in a square root. We did talk about this actually 2 weeks ago as well. It's not technically a substitution. Instead, you're going to use the double angle formula, which we've written up before. This time, you've got to be a little bit careful. I just leave it in the form that I had before. Cosine squared x is 1/2 1 plus cosine 2x and sine x as before. I want you to, these are the forms to remember it in because that's what we needed for the trig powers. But actually, in this case, you kind of have to change the x here, the 2x. You change that to an x, and here you change this to x over 2. Then you can take the square root. That's a pretty obscure sort of thing, but if your integral involves one of these, it may be that you need to use these double angle identities. On the other hand, if you end up with 1 plus sine x or something on the denominator in an awkward place, multiply and divide by 1 minus sine x. See, if you have 1 plus sine x times 1 minus sine x, these two together become 1 minus sine squared x, which can be then written as cosine squared x. And that could make your denominator a lot easier to deal with. So watch out for that. Of course, there are different permutations of this. If this was instead 1 minus sine x, you would write 1 plus over 1 plus. If it was something like 1 plus tan x, well, you'd do 1 minus tan x over 1 minus tan x. No, you wouldn't. That wouldn't work. You get tan squared x minus 1. I'm sorry, if this was secant x, that's what I mean to say, then you'd multiply by secant x. So let me just write this. Secant x plus 1, say. You'd multiply by secant x minus 1 over secant x minus 1. I'm assuming this is on the denominator, of course. If it's in the numerator, you can already split it up into two integrals. If it's in the denominator, then you might be able to get some relief by multiplying by this conjugate here, and you'll get secant squared x minus 1 on the denominator. And you can replace that by tan squared x. So you'll use secant squared x minus 1 equals tan squared x, and then you can split up the numerator instead of the denominator. You're not allowed to split up the denominators, you see. So that's why those techniques can be handy. All right. A few more techniques that we had covered. Let's see what else we have. Some of these I didn't really go into such detail, I guess. But the old arm's getting tired. There we go. What else we got? Well, something I definitely didn't talk about is how to do integrals that look like this. Cosine x, cosine mx, cosine nx, or maybe sine here or sine there. This is described in section 19.1, but it's actually not in Math 104, so I didn't talk about it. So hopefully ignore these. It used to be in Math 104, and if you look at very old papers, you might find it. Of course, if you're watching online doing a different course, you may in fact have to know how to do these, so you're going to have to read up on it. On the other hand, something that you do need to know in Math 104, powers of trig functions, learn the techniques that I spent the first 45 minutes of this class dealing with. If you have a square root of a quadratic, maybe complete the square. If there's a linear term, then substitute, just as we did a few minutes ago. And trig substitution is probably what you want. Again, you will have checked, following down this sort of vague checklist here, that there is no obvious substitution. Because if there was, you should, if there is, you should do that instead of the trig substitution. And of course here you've got to know your types and your templates. If none of these things worked, by the way, it seems like a lot of techniques, but you can more or less eliminate most of them. Check of obvious substitution, but then the rest are very specific types, mostly involving trig functions. So if it doesn't seem like anything else applies, if you have the integral of a product of two things, two or more things, maybe try integration by parts. That can often work. And just to summarize what I said verbally, I guess, as opposed to said writing down, doesn't make that much sense. Okay, so to summarize what I spoke of a few weeks ago, when you integrate by parts, you have to choose a u, and you have to choose a dv. And in order of sort of, what would I like dv to be? Exponentials is better than trig, is better than powers, is better than log, and inverse trig for that matter. So u, this is good, and this is bad. dv, this is good, and this is bad. Actually, nothing is really bad for u. It's really, nothing is bad for u. No, nothing is bad for the choice of u as long as you can differentiate it. But the dv, it's critical that if you have an exponential, you pick it. I mean, that's good. And it's really bad to let the dv be log. On the other hand, if u is a log, then you can differentiate it and get rid of the log. Logs are pretty evil. This, of course, applies not just to a product of two things, but as you might recall from 2 weeks ago, it also even applies to just log x or inverse trig. Any inverse trig, not just inverse tan, or a power of logs. Even though it's not a product, you just let this be u and this be dv. Same with the inverse trig stuff. Same thing works for a power of log. All that integrate by parts. That's a sort of nice rule of thumb. And then try a non-obvious substitution. If you can't integrate by parts, nothing else seems to work, then you might really have to get serious and try the kitchen sink of substitutions. Try anything you can think of. An example of that might be that sixth power that I wrote up that you asked me about. What if you have a square root of a sixth power or something? And I said, well, try the cube. Get it to a trig substitution. That is something clever. And, you just have to think of it. I wish there was some method that solved every integral. But the fact is, most integrals that just pop up. If you just write the integral of just some function that you think of, probably you won't be able to do it. Probably you won't be able to do it if the function is sufficiently complex. I mean, even something like this. Not cosine squared x, but just cosine of x squared. You can't do it. You can do it as a series. You can do it as an approximation if you make it a definite integral, but there's no integral. And yet this comes up there's no simple way of writing that. And it comes up in optics and probability and all over the place, called a Fresnel integral. So it's just sort of frustrating that integration is much harder and much more impossible in a way than differentiation. So basically then, what you need to do, in addition to practicing the techniques at the beginning and all the trig substitution, is at some point before you take a quiz or an exam, a midterm in this, you need to subject yourself to a grab bag of integrals. You need to get some sample of integrals, not by topic. Just, they exist in the textbooks. In your textbook, every textbook should have a grab bag. My book doesn't have it because it's not a textbook, it's a study guide. But nevertheless, even online you can find repositories of these things. You've got to do, like 20 or 30 or 100. When I went to high school, we had to do 100 integrals for homework. I kid you not. That was in Australia. 100 random different types that fall into these categories. So that is how you master this topic. But then the good news is that actually, once you get experienced at it, you should have confidence to do almost any of them. Just like you can pretty much do derivatives, I hope, having had a lot of practice. So the integrals should end up being fairly easy points, because the rest of the course is actually harder. This is more algorithmic. So practice, practice, practice. Any questions before we finish? We have a few minutes, but I'm not going to say anything else unless someone has a question. No questions? Then we're done. See you next time.